Thanks for watching. In this Intro to Networking video, we will talk about network theory and explain some common network gear. We will define network terminology and take a look at what's going on behind the scenes. I will also show you a few hands-on things that you can do today, because I don't know about you, but I learn better by doing stuff hands-on. So, I hope you enjoyed the video, and if you do, don't forget to like the video and subscribe to the channel. It really does help. Thanks. A computer network is a group of devices that are connected and can communicate and share resources. Devices can include PCs, servers, printers, TVs, and even devices like gaming consoles and smart home gadgets, like toilets. Wait, here, toilets? Yeah, toilets. LED lighting, heated seat, everything you always ever wanted in a toilet. Now, let's talk about how these devices connect. And to do that, let's dive into a bit of theory, specifically the Open Systems Interconnect model, or OSI model for short. This conceptual framework breaks down network communication into 7 distinct layers, each with its own role. Understanding the OSI model can be really helpful when things go wrong. And notice I said when they go wrong, not if, because things will go wrong. It's just a matter of time. And when things do go wrong, knowing which layer the issue occurs in can help you do a better job of resolving problems. Let's start with the foundation layer. Layer 1, the physical layer. This layer is all about hardware connections between our devices. Think cables, switching router ports, and network cards, all of the physical stuff that links everything together. But don't forget about electrical signals, light, and wireless signals. It's all about transmitting raw data in the form of bits, those ones and zeros that let the digital world communicate. Layer 2, the Datalink layer, is all about local network communication. Here the bits, the ones and zeros from the physical layer, are organized into units called frames. This is where switches primarily operate, directing traffic on your local network using MAC addresses. In this layer, data frames are neatly organized and forwarded to the correct device, ensuring efficient communication within the same network. Layer 3, the network layer, handles data transfer in the form of packets. Routers use IP addresses to route packets between networks. In this example, routers are deciding where to send the packets, shown in yellow. Sometimes these decisions are straightforward, like directing traffic between a few routers. But as networks grow, these decisions become more complex, involving many routers and networks. One thing to remember though, routers only pick the next step for the packet. They don't schedule the entire path that the packet is going to take. Layer 4, the transport layer, acts like a traffic controller for data. It divides data into smaller segments for transmission using protocols like TCP or UDP. It also manages port numbers, which help direct the segments to the correct application on the receiving end. TCP ensures reliable delivery, error correction, and flow control, keeping everything nice and neat. But then there's UDP, which is all about speed. It doesn't care if everything is in the right order or even if it arrives at all. Layers 5 through 7 focus on managing data for applications. The session layer establishes, manages, and terminates connections. Next, the presentation layer translates data into a readable format for the application layer, handling encryption and compression. Finally, the application layer is the interface between applications and the network, enabling tasks like web browsing, emails, and file transfers. Now, let's see what some of these devices look like. A network card or NIC connects your device to the network either through a wired connection or wirelessly. Each NIC has a unique MAC address that helps identify your device on the network. NICs operate at layer 1 of the OSI model. A switch is a device that connects multiple devices within the same network, allowing them to communicate efficiently. Since it operates at layer 2, it directs data to the correct device by using MAC addresses, ensuring that information gets to where it needs to go quickly. There are some switches that operate at layer 3, but we'll get to those in a future video. A router connects multiple networks together, such as your home network to the internet. Operating at layer 3 of the OSI model, it directs data packets based on their IP addresses, finding the best path to ensure they reach the correct destination, whether it's to another network or out to the internet. Visually, routers normally will have fewer ports than switches. A firewall acts like a gatekeeper between you and the internet. It lets the good stuff in and keeps the bad stuff out. It also makes sure that valid requests that go to the internet are able to get back in. On the left side, we have a logical view where bad packets, represented by little skulls, bounce off the firewall. But let's dive into what really happens behind the scene, not just this logical view. On the right side, the firewall examines incoming packets through the WAN interface. If they're dangerous, they just blow up inside the firewall. Well, maybe not blow up, but they get discarded. The good packets, like parts of emails or documents, pass through safely and are directed to the correct server. Every device connecting to a network has a MAC address. Even your phone. Well, maybe not that phone, but this one does. A MAC address is a 6-byte, hard-coded, unique identifier assigned to a device's network card, or NIC. The first 3 bytes, known as the OUI, indicate the manufacturer, like Cisco, Apple, or Tesla. MAC addresses are globally unique, meaning each one is distinct worldwide, like a fingerprint for your device's network card. However, they're only significant on the local network that they're connected to. Think of them like apartment numbers. Within the building, apartment 103 helps you find a specific unit, but elsewhere in the city, it doesn't mean much. In the same way, your MAC address helps you identify your device on a local network. But outside of that network, it really doesn't mean much either. IP addresses are composed of 4 bytes, like this. They are unique identifiers for devices on a network and the internet. Think of an IP address as a digital street address, not just for the internet at large, but also within your local network. While a street address helps mail find your house in a big city, it's also necessary in a small town. These addresses play a crucial role in routing, which is guiding information across networks to its intended target. Without IP addresses, the internet as we know it would not function, as they are essential for connecting our digital world. When your computer or device needs to access something beyond its local network, like another network or the internet, it uses its default gateway. Think of this gateway as an exit door from your local network. At home, this is usually your router or modem directing traffic to and from the internet. But in an office setting, the default gateway is typically a more robust router managing traffic between your local network and other networks or the internet. Your device doesn't know the entire path to the internet, but it knows that this exit can lead it there. Let's pull up some important network details from Windows. To do that, we'll use the command prompt. First, click the Start button, type CMD, and select Command Prompt from the results. Now, we'll type IPconfig /all. You might need to scroll up a bit to find the right network card, which is going to be the one with an IP address. And there are 3 key pieces of information we're looking for here. Number 1, the physical address, which is the MAC address at layer 2, the IP address, which is layer 3, and your default gateway, which, remember, is your computer's door to the internet. The ping utility is like a simple conversation between devices. Imagine one computer sending a message saying, "Hey, are you there?" If the other device is online, it responds, "Yes, I'm here." But if there's no reply, it means the device might be unreachable. It's a quick way to check if another device is accessible on the network. The other thing that ping gives you is the amount of time in milliseconds that it takes the packets to make a round trip between the 2 devices. With these things in mind, let's again type a command from the command prompt. I'm going to type ping 192.168.1.118, which is a server IP on my local network. We see the replies so we know the server is up. But is that really all that's going on here? Just pings and replies? As it turns out, that's all we can see, but that's not all that's going on. We know that local network communications rely on MAC addresses, not IP addresses, for communication between devices. So what happens if a computer has an IP address, but not a MAC address of the server that it wants to contact? When this happens, the computer uses Address Resolution Protocol, or ARP, to broadcast out an ARP request to find the MAC address of the server with that IP. Then the server with that IP address responds back with an ARP reply and says, "Here's my MAC address." Now that our computer has the MAC address for the server, it is able to ping it. It sends the ping request to the server and then waits for the ping replies to come back. Hey, do you need even more network learning right now? Here are a few more things that you can try on your computer. I hope you enjoyed the video today and learned something. One thing that I can tell you is that if you understand how ARP works, you now know something that most people in IT don't know. The next videos will continue to teach networking, but each will be a deeper dive. And, as always, I'll see you in the next video.